Okay, so I'm going to start off with what gets me out of bed in the morning, and it's about building infrastructure. I'm a civil engineer by training, and the thing I like to do is plan, design, build, maintain infrastructure. And it's that infrastructure that provides our quality of life, clean water, food, the movement of goods and people, the housing of goods and people. And that's what provides our quality of life. That's what excites me. And what better material to build good quality, resilient infrastructure is concrete. And the best concrete to use for that is ultra high performance concrete. I'm not saying that everything needs to be built by the UHPC, but there is a market and a demand for a very resilient concrete material to build very resilient infrastructure for society's quality of life. Okay, so I'm going to talk a little bit about UHPC. I'm sure a lot of people in this room know very well what it is, and there may be other people that don't understand that much about it or know what it is exactly. So I'll just talk briefly about a definition and some properties very quickly. Then I want to go into the nanophysics and the chemistry of UHPC, but I'm not going to go anywhere near as deep as the chemistry that I just saw in the previous two presentations, but I will touch on it a little bit. Then, what is carbon nanofiber in terms of how we manufacture it and how we get into the concrete? And then I'm going to do my project comparison. Okay, so what is UHPC? It's the cementitious composite material with enhanced strength, durability, and ductility compared to the performance of high-performance concrete, for example. It contains fibers normally, street fibers at the micro level, minimum compressive strength of 17,000 psi at 28 days. It has, it's formulated with very fine materials which gives you particle packing, it's a very dense matrix. It has a very low porosity so that gas and liquids cannot migrate within the matrix. It's an order of magnitude less permeable than high-performance concrete and 2 orders of magnitude less permeable than normal concrete. And that's what gives it a lot of its durability properties. All of the durability properties you can measure in conventional concrete or even high-performance concrete, UHPC is typically 1 order of magnitude superior to that. So you have a very durable matrix. But one of the also properties that's very important is what we call post-cracking ductility. So when you put concrete in tension, you have a brittle failure. It cracks if you launch a rupture, and you have a failure. You put rebar into that. In UHPC, we put microfibers in the matrix. The microfibers are actually stronger than the matrix. So once you crack the matrix, you engage the fibers, and then the fibers are stronger than the matrix, so they bridge the crack, and as you continue to load it, you'll see other locations in the matrix will crack, and you'll end up with a well-dispersed series of micro cracks, until finally you reach the capacity of one of these cracks where the fibers will start to yield, and then you will get a crack localization, and then a softening or a reduction of strength beyond that point. So it is pseudo-ductile when you look at it compared to steel, and it's a similar stress-strain relationship, and that's one of the properties that makes UHPC very interesting for design structures. Okay, so that's a little bit on the material. I don't want to dwell on that too much. That's not the purpose of the presentation, not to make you experts in UHPC. So we introduced carbon nanofiber into our material. And so as everybody knows, coal is carbon and so is diamond. And so it's the structure, microstructure that's different. And as we saw, a lot of people previous speakers talking about graphene. So we can have nanocube, or we can have nanofiber. And in our technology, what we manufacture is a nanofiber. And so the nanofiber is typically in the range of 50 nanometer in diameter that we manufacture, and anywhere from 100 to 200 nanometers in length. So we had a lot of presentations already, so I won't spend much time on what is carbon nanofiber. I think most people in this room know what it is. What I do want to talk about is how we commercialize it, how we get it dispersed into the concrete. Because as I've already pointed out, that's the big challenge in industrializing the technology. So we take carbon vapor, we put it into a reactor in our factory. We manufacture catalysts, different oxides and catalysts. We manufacture with ball mill, we manufacture different catalysts. We put the catalyst in the reactor, we put the carbon vapor into the reactor, and heat, and we convert the carbon vapor into a carbon nanofiber. So out of our reactor comes an agglomerated dust. And this is done in a controlled environment in a sealed chamber in the room. Because if you take that grab a handful and blow on it, it disappears before your eyes because it's nano scale and you can't see it. So we collect the agglomerated carbon nanofibers from our reactor. We move that to another part of our factory, and then we disperse it with high shear mixers, dispersants, and superplasticizers and some antifoaminases, and we make a black paste. So we actually liquefy the carbon nanofibers in suspension. We put that into a pail, and we ship those pails around the world to our various locations that we're actually going to manufacture. Because all of the rest of our materials, all the five forms of concrete, are sourced locally. And our target is to be within 150 miles of any project that we source out the rest of the raw material. So about 0.4% of the UHPC, which is the paste, is shipped globally. And the other 99.6% is locally sourced, as close to the project as possible. So that will be the cement percentage that we blend up and put into the bulk bag and fibers, steel microfibers for the post-product of our building. Okay, so once we have that paste, we'll put that into the UHPC along with the other materials to make it. So that's how we actually disperse the carbon nanofiber into the throat we mix. So what happens is we take that pail of paste and we dilute it in the mixed water. And that mixed water is put into the mixer with the sand, cement, and microfibers and mixed. And every cubic yard of UHPC, we have approximately 5 times 10 to the 19 carbon nanofibers. So we have approximately 8 carbon nanofibers to surround every single particle during the hydration process. So this is when we manufacture the carbon nanofiber, our process is designed specifically to enhance the surface of the carbon nanofiber, to enhance the bond with the calcium silicate hydrate. And that is what we spend a lot of time in our reactor trying to perfect. I should say, maybe perfect is the wrong word, but what we try to do is a highly effective carbon nanofiber. And we specifically look at modifying the surface so that the fibers are actually affected by that condition in order to enhance the mechanical bond and to make the carbon nanofibers perform better in these contexts. So here we have a transmission electron microscope image of two pastes. One that has carbon nanofiber on the right, and on the left does not have carbon nanofiber. And you'll notice that adjacent to the calcium, tricalcium silicate, it's very granular looking on the left, whereas on the right, it's less granular. And so this is an indication of porosity in the transition zone next to the tricalcium silicate. And so the carbon nanofiber actually enhance the interstitial zone, densify the interstitial zone, and improve the bond of the C3S into the sand particles or the microfibers as well. So here we have it's a high angular dark field scanning transition image of hydrates through an air bubble or an air pocket within the matrix. So the black is air, and the hydration products are the lighter color. And what you'll see is a carbon nanofiber that's going through the air bubble to both sides of the matrix, the hydration products. What we've found is that carbon nanofiber has significant improvement on a lot of mechanical properties of the UHPC. One of them is shrinkage. We notice a big drop in the shrinkage in the UHPC. And part of the reason is the nanofiber set up a skeleton within the matrix and resist the shrinkage that occurs, particularly as the product of water is consumed by the products of hydration, or the hydration process. So these nanofibers actually reinforce that space and resist the shrinkage that would normally occur during the hydration process. So what does it do, what does carbon nanofiber actually do for the ultra-high performance concrete? Well, during the early hydration process, they act as nucleation sites and facilitate a more uniform hydration. And that uniform hydration reduces the differential stresses in the matrix during the hydration and contributes to higher restraint in our mixes. So we end up with a very high restraint development in the carbon nanofiber in the matrix. And it also has better control on the setting characteristics. So we have better working time, hot life in the field. So we notice that we can actually have our material batched at 95 Fahrenheit in the field, and it'll communicate workability across an hour. But once the hydration kicks in, the hydration goes more uniformly and develops a higher restraint. Nanofibers also help to strengthen the tensile properties because all tension cracks initiate at the nanoscale. So if you nanofibers bridging the nano cracks, you delay the onset or you raise the modulus or effective modulus of rupture in tension. So we end up with a higher first crack and modulus of rupture in the matrix. And because they densify the interstitial zone next to the microfiber, you end up with a higher bonded microfiber and a higher ultimate tensile capacity post-crack. So this shows the early shrinkage in the material. And you'll see that we're at about 360 micrometers per meter of shrinkage, which is about close to half of what you'll find in UHPC that does not have carbon nanofiber or some other shrinkage compensating admixtures. Okay, I want to show an example of 3 bridges and talk a little bit about the embodied CO2 over the life cycle of the bridge. So the life cycle of a bridge, obviously, there's in the construction, you have materials, you have labor for fabrication, you have labor and equipment for erection, and then depending on the length of the project, you have the cost of money that's involved in the project. During the operation of the structure, you have operational costs, repairs and maintenance, and then anytime you do repairs and maintenance, you have to take that structure out of use, fully or partially, and so there's a loss of use cost to the owner of that structure. So what I want to show you is that using UHPC in the solution compared to a conventional bridge solution can actually create value for the owner over the life cycle of the project. This also corresponds to the CO2 over the life cycle of the project. So it's not only money, it's also CO2. So here's a conventional concrete solution. We have some precast girders. These are ASHO type 4 pre-stressed bridge beams. So we have concrete, we have precast plant, we have reinforcing, and we have post-tensioning or pre-stressing strands. And we make a girder out of those and put the girder in place. And we have ready mix and rebar. We use a cast in place deck. And then on a cast in place deck like this, we may put a membrane and a layer of asphalt on top of the right. So that's a conventional solution. So I took this is a design that was provided to me by the Virginia Department of Transportation. This is a VDOT span for approximately a 100-foot single span bridge. And so I'm going to look at this section, which is about 25 foot wide, 100-foot span with 4 ASHTO girders and a cast-in-place deck with asphalt on top. And now compare that with a steel girder bridge. So it has a well-wide flange. This is the metric size, 1,100 millimeters by 291 kgs per meter. We're going to have 4 of those. We're going to have steel diaphragms for load distribution. I should have mentioned that the precast girders are concrete diaphragms for load distribution. We'll have the same deck, cast-in-place deck, ready mix, rebar, and cast-in-place. Again, 100-foot span, 25-foot wide, and that's the another conventional bridge for this type of. And this again is the VDOT design. And then I'm going to look at the UHPC solution, which is an optimized pie girder. And this was a study that was done by MIT on optimizing the pie girder shape. So we're going to manufacture the UHPC with microfibers and some pre-stressing strands to put the girders together. Again, 100-foot span, 25-foot wide. So, so I have here worked with all the quantity of materials all the concrete, the steel, the UHPC, the asphalt, membrane for the three solutions. So these are the actual quantities of material in either tons or cubic meters, and I think I'm running out of time, so I'm not going to get into the numbers exactly here. And here's the embodied CO2 in each of these materials. Now, I had to pick a site because what the actual CO2 is in place is a function of where you're building a bridge. So this is a location in Vancouver because I had done this presentation previously for a group in Vancouver. And so here are the embodied CO2 for carbon, UHPC, steel, and asphalt in the Vancouver, British Columbia, Canada location. And now I'm going to take the quantities of each one and the CO2 per unit and come up with the total CO2 for the solution. This is 124,000 kgs of CO2 in the steel solution, and we have 75,000 in the precast solution, and in the UHPC solution you'll see it's 41. So it's about a third of the steel and a little more than half of the conventional precast solution. Now I also want to look at the impact on schedule. So with an all precast solution we can save time. And I just assumed a very conservative number. Let's say 1 week, and we had to detour the traffic a couple of miles around while we're building the bridge, and we had 10,000 vehicles per day. You have to pick some numbers. It's site-specific, project-specific, but in this case, that's what I chose. We have 2.25 kgs of kilogram emitted per mile, per kilometer, per vehicle. So we can calculate how many kgs of CO2 is emitted by saving 1 week on the schedule. We saved 35,000 kgs in the project from construction traffic. So then again, I plugged that into the table. I started off with the CO2 from original construction. The savings form a 1 week faster schedule, and I end up with a net number which shows that we're now at 10% of the conventional solution at this point. Now, if we look at over the life cycle, and we look at, we're going to replace the deck once in the two conventional solutions in a 50-year life. That's 60,000 kgs to replace the deck and the asphalt membrane. And again, I put that in here, so I added an extra CO2 for operation and maintenance. And what you find out, what you find out is that we're now at about 5% of the conventional solution over the life cycle of the project. So you can dispute any of the numbers you want, but the difference is so great. You know, we're talking almost an order of magnitude difference in the life cycle of the project in terms of CO2. It's a significant saving, and it's one of the things that we don't look at enough going forward. And I'm the chair of ACI 239, and we have a sustainability committee, and these are the types of studies we're going to be taking up to prove that concrete solutions, particularly UHPC solutions, over the life cycle significantly lower the CO2 emissions. We need to get that down to zero. I guess if we go another 50 years, apply a negative for saving construction traffic, we'll be in negative numbers. So I want to just conclude by seeing the advantages of a UHPC bridge. We reduce the amount of cross-sectional area and quantity of materials. We eliminate passive reinforcing steel. We reduce the formwork, we reduce the crane time, construction time. We eliminate the waterproofing because of low porosity and permeability of the material. We don't need corrosion inhibitors or epoxy-coated rebars. We can reduce the foundation because of the lighter mass. It has a lower environmental impact. Operational maintenance is reduced, and the seismic performance is improved because of that coated material. Thank you for your time, and I don't know what time.